Nalco has got a lot of benefits through this system, which is called the sequence of events. There are some modules which are capable of giving a timestamp for a particular input or for a particular output. So when imagine there is a problem in the turbine and the turbine trips. So we need to find out for what reason the turbine has tripped, because everything is automated. You get a lot of inputs and outputs with which you can analyze why the turbine or the boiler has tripped, or it has failed, or it has now come to a shutdown. So the sequence of events, there are some modules with this capability which are able to register all the events in a time sequence as to which event happened first. Hope I'm able to make you understand. The sequence of events module have the capability to stamp the event's time. Imagine at 3:22:36 seconds, at 3:22:36 seconds and 102 milliseconds, lube oil pressure has become low. Then this sequence of events module is able to timestamp that particular event to that particular time. And when you get the sequence of event report, it's so interesting to analyze that, okay, this has happened first. This is the root cause, followed by these events, and then this, finally, at some point of time, maybe if there is a 10 seconds time delay, you will be so interested to see that after 10 seconds of that particular thing happening, exactly the turbine would have tripped. Okay, not in the case of lube oil pressure, but in some other cases where we have 10 seconds of time delay for something to, or for operation engineers to take control and maybe change the process. So hope you are able to understand. In case you have this sequence of events recorder, it's very easy to analyze, or it's very interesting also to analyze as to which event happened first, followed by which event, and if there is any logical time delay which has been already done, has those things happened exactly as we had intended? Everything is easily possible to be analyzed. So this is one another feature of DCS, which is very, very unique. And as I told you, there are so many other features which I'll be explaining as we go fast. Okay, then as I told you, we have input output modules. They are of different kind. Normally it is the 4 to 20 milliampere current input, and one particular module category, the third one which I have explained here, is the thermocouple or RTD, which is specific for temperatures. That's why I had put it separately there. Now, these analog output modules, they are also mostly giving 4 to 20 milliamperes. In some other cases, it will be giving you 1 to 5 volts. Whereas this digital inputs and digital outputs will be 24 volts and output or input. Okay. So these are all different kinds of modules or cards, electronic cards, which will be receiving each input from the field. DCS modules are mostly having 16 channels. These black color, these modules which I have shown you in the picture, they're all having different channels. Each channel can have one parameter. Imagine it is an analog module. Imagine it is an analog input module. This channel, there are 15 channels, as I have explained it here. In 15 channels, you are able to analyze at least 15 pressure transmitters, or a combination of pressure transmitters and flow transmitters, or any other transmitters in the field. Each of the transmitters giving a 4 to 20 milliampere signal. So at least 15 parameters you are able to access through one card. But ideally, we don't use all the 15 channels. We give some spares so that any problem happens, we will be able to use the spares available within the module. And not only that, any particular control will not all the parameters will go into a single card, single module, because one particular module fails, then the entire process of that particular thing fails, right? So we will be distributing it in such a way. That is where the typical engineering comes. So where to allocate which input, how to distribute it in such a way that by the failure of single input module, nothing catastrophic for the power plant will happen. So those things are called the engineering. So any input or any output is designed in such a way that at least we will have some spare channels in every module, and the controls will be grouped in such a way that not all the parameters of a single equipment goes into one module. So we will be distributing it into many other modules. So this is a glance of all the IO modules, input output modules, which are inside the node. node of the distributed control system. As I've explained to you, this distributed sequence of events, this is also very, very important. And interestingly, that has got 1 millisecond resolution. Every millisecond it is able to sense presence or absence of an input. So when you see the sequence of events report, you will be able to find that at 322, 36, and 102nd millisecond, one input has come, and 103rd millisecond, another input has come. So that will be very, very helpful. Okay. So this is the architecture of the sequence of events. They have time stamping, and interestingly, we take the time from satellite. So the advantage of that is, in case there is a total power failure in which all the 10 units or all the running units, maybe 8 units of a single power plant collapses. So which unit has tripped first, or which units, which problem has occurred first, that is also accessible through, or that is also we are able to analyze through our DCS. How are we doing it? Every unit is taking its time from the global positioning GPS, that is the satellite, and from that all they have their own network interface module and timekeeping module, the TKM. They're all taking care of the time synchronization of all the units. At any point of time, every computer of all the 10 units will be showing the exact milliseconds also. So that way, time is very much important, because sometimes unit 4 will be the cause for the whole problem, whereas you will be thinking that there is, because of the time problem, you will be thinking that some other unit has tripped first, and that has only caused the problem. But this time synchronization, along with the sequence of events, okay, which takes care of the timestamping, it is easily understandable as to at what time what had happened in case of all the units having a problem, or even a single unit having lot of parameters which are disturbed. As I told you, apart from IO modules, we have the control and communication modules also. Control and communication modules, we are not going to go into much, but without these things, they are not able to communicate with the control network. As I told you, any node should sit on the control network. So they will have their own network interface modules, and they will have the rack controllers. So unless the network, the control network interface modules are there, whatever processes are analyzed within the processes, whatever inputs are received, they are not able to be meaningfully controllers. So this is how controls and communications take place. Okay. Now there are so many things which we can understand, but basically every this is a peer-to-peer communication. Okay, this is a combination in which we have something called a network interface module, network processing module, and then something called a bridge controller or a controller. Here they're always redundantly available. There's NIS and NPIM also, because we have two control networks. The control modules are also redundant. If one module fails, other modules automatically take place. The controllers and control network, the communication modules are all redundant. At any point of time, any one network fails, only that particular network fails, but the power plant keeps on running. And in case that is very important, we request for a shutdown, or whenever there is a shutdown, we immediately replace all the faulty things, and we try to rectify those problems. Now, this BRC, inside this BRC, all our engineering logics is stored. As such, you do it in a computer. Once the project is completely designed or engineered, the entire logics or the project has to be stored into a controller, or the heart of DCS, which is the processor. So this is for a particular node. As such, as I told you, for turbine, you will be having a separate controller or a processor. So all the turbine related logics will be into that particular controller. In the case of boiler, you will be having it in a separate controller. And in the case of balance of plant, you will be having a separate controller. So many thousands of function blocks will be used for these purposes. In DCS, there is one thing very interesting is many are already tailor-made standard function blocks. Tailor-made standard function blocks. Imagine you want to start a pump that has already got a block which will receive the on-off input of the pump, and that particular block will be able to issue a start or stop command. In case after starting the start feedback is on feedback is not received, that module will be this software block or the function standard function block will be capable of giving you an annunciation saying unsuccessful start, or when you put it off, if there is no off feedback after some few seconds or whatever time you have defined, then that is also immediately this block itself is capable of doing all that. So what I mean to say is, when you buy a DCS or when you are working in a DCS, you don't have to break your head to make all the basic function blocks of and or not, so many combination of gates and all. You don't have to break your head and do it. Hope as engineering students you understand that we are very much into AND gates, OR gates, NOT gates, NAND gates. For all these things, then only you will ultimately get into a function block. If you want to make a small logic also, just as I was explaining you the water tank in our home, in case water level is low and the pump has not started it, then only we have to start the motor, the motor in our home. So for that reason, you need at least two inputs. Water level is low and your motor is not on. So these two are put into an AND gate, and the AND gate output is not one, then only it will go for a start. So similarly, there are so many things which will be needed to take care when a pump has to start or when a pump has to trip. So those are called permissives. So based on certain permissives, a pump will start. Based on certain permissives, a pump or motor will stop. So these standard function blocks, they are capable of taking into lot of inputs, and you don't have to logically, physically sit and design each and everything. These have already been done by the manufacturer of the DCS. So they are giving you certain important function blocks which are capable of handling so many normal situations. And in Nalco specifically, when we go into certain areas, we have also designed certain blocks which were not at all available in the DCS. We have designed certain new controls where we needed specific controls which they have not envisaged. The original equipment manufacturer of DCS, they have not envisaged. So those things are also possible. But then ideally, most of the standard function codes, function blocks are already tailor-made, and it's all available as function blocks inside the DCS. It's a software platform. So whatever block you want, you can just drag and drop, and then you can start doing the wiring, and then you can keep doing the engineering, control engineering. Okay. So this I've already explained to you. For better understanding, I've kept it as a separate slide. We have now going ahead with DCS control and communications. The capability of the DCS is, the DCS at least where we are having right now is, it can at least host 250 nodes. I was talking to you about 7 nodes in Nalco, but the capability of the DCS that Nalco is having is, each single unit DCS is capable of handling 250 nodes. So you may be able to understand how much it is underutilized. Like in the place of 250, we are using only 7 nodes. But you may be thinking in your mind, sir, why don't you put all the 10 units in a single DCS? That is not possible, because the failure of one DCS will cost all the 10 units for Nalco. The power generation of all the 10 units will be at stake. So that is why we don't do that. Hope you are able to get me. Okay. So though the capability is high, we are utilizing it to the best of the possible, because with less load, what happens? Speed increases, like the speed of performance, not beyond the manufacturer speed, but then at least it takes you to the highest speed which is possible. Okay, with that we will go ahead. So as I told you, even the bridge controllers and everything are all satellite linked or GPS linked, from where you get the time. So time synchronization is very, very important. Okay. Now going ahead, as I was telling you, engineering tools are very, very important. Engineering tools, what I mean is how you achieve the engineering of the logics. Every particular equipment. Now, when an equipment manufacturer, imagine in India, we have Bharat Heavy Electricals Limited, BHEL, who is the manufacturer of a turbine. The turbine, when they manufacture, they have something called a control philosophy for the turbine. So the control philosophy of the turbine will explain how the turbine has to be controlled. And that control philosophy has to be translated into logics by using different gates or function blocks or whatever. And that particular logics needs to be translated into a form which is understandable by the DCS, or through the engineering tools, you may have to do it inside the processors. So as I told you earlier, the engineering station is also seated on the control network, and it is also able to capable of communicating with the operations network. Okay, so that way inside the engineering station. Now engineering station is a for those of you who have not visibly seen an engineering station, it is just a software platform where your every processor in the DCS is separately visible, and whenever you open a processor, you are able to access it in forms of a file, Excel file or a Word file or something like that. Okay, so it opens and you can put all the function blocks that are needed, and you can assign input modules, output modules for that. Once a logic is formed, you need some inputs, and based on those inputs, you will be giving out some outputs. All these can be put in some sheet. So something similar to an Excel sheet, 1, 2, 3, you can be making a lot of logics. And when you do a compilation of the project, what you have done, if there is any logical error, just as we were all doing it in C and C++ programming, if there is any syntax error or any other logical error, during the compilation, it will clearly tell you that this is an error which cannot be overlooked. So you need to modify it suitably. In case there is not an error, but it's a warning, it can be overlooked. It will also show you as these are capable, or these are all the warnings which your system has got. Imagine you are generating an output and you're not connecting it to any output module at all. That is not a big error. That will be shown to you as a warning. Okay, but in the place of an analog signal, if you are using a digital wire, that is a digital line, that is a error which cannot be overlooked, because you cannot take an analog signal in a digital wire. So in case of a in case of a error, it will not allow you to go further ahead after compilation. It will stop while compiling, and it will say you have compiling errors and you have to rework on it. So that way the system is foolproof when you do it in the engineering stages itself. Of course, there are logical problems which we can make, logical misunderstandings between engineers, and understanding the control philosophy can be there. But then basically, the system is designed in such a way that you don't make any mistake while doing the projects or while doing the engineering inside the computer and then loading it into the processor. So ideally, once your engineering is done, it needs a lot of timing. Like as I told you, it will be having a sheet and you will have to work on it very hard. It will take maybe months for you to design logics for one particular control unit of CPP. Once it is done for one unit, maybe you can duplicate those logics into for the other units. But then at least for one unit, you need to be really working very hard. So as I told you, this engineering server that will take care of all the logics. So this is a logical human machine interface, and the workstations which we were earlier seeing was a graphical human interface. Okay, so hope I make you understand. The operator workstations are the graphical human interface. The engineering station is the logical human interface. For the logics which are inside also, you need a human interface, but core of electronics and instrumentation, especially you people who are listening to me, you will be core involved in this engineering stations, where the logic needs to be interpreted in a way that computers will understand, and the control philosophy given by the equipment manufacturer is all put inside. Okay, then our ultimate aim is to give everything to the operators, that's the operation engineers, who will be graphically, visually seeing the things and then doing it. So in case there is any problem, in case one pump is starting and another pump's current is showing, they will immediately call you and say, Arey, you have given a pump, and when we are starting this pump, the current of the other pump is only increasing. So then you need to analyze whether you have made any logical mistake in the engineering server, and maybe you may have to replace those things. Hope I'm able to practically put it to you. I'm sure it's not easy for you to visualize everything, but then we will try to understand. Okay, communication. So this part, engineering tools, I think when you get a chance, if you get to visit any power plant, either in your summer training internship or apprenticeship, please take time to visit an engineering station, which will help you. Apart from that, now there are, as I told you, there are so many blocks and everything. As this is a typical picture of our engineering station. So this red cross marks below, they are the errors, which cannot allow you to compile more. Then you have different projects, and in the projects you have different sheets. Each sheets are called control logic sheets, and they have different names. So in a way, it will look like a maybe a compilation of many Word files or many Excel files put together only. But then when you open it, it will open in their own application software platform only, and inside that you will be able to find out the logics. Okay, done. So this part, engineering tools, I think with this you can have lot of capabilities. As I told you earlier, for every parameter you can generate an alarm. For every parameter you can generate a color change. Imagine the normal operating pressure of power plant is 0 to 145. Beyond 145, if you want the color to become red, so that operation engineers will get alerted, those things are possible. You can change colors. You, as soon as it becomes more than 145, you can generate an alarm. And some places where it is very dangerous, you can give a human voice alarm. Some recorded human messages can come out, like in your railway stations and all. You have recorded voice messages. So many things are possible in with DCS. So engineering tools is the core of engineering, and it is basically the responsibility of C&I or E&I engineers. So you will be you will be finding it interesting in case you get to work in a plant like this where you want to design things. Okay, there are so many other features. As I told you earlier, these function codes are all, whichever is shown in this sheet, these are all predefined. They're all given by the manufacturer, like the DCS manufacturer. So it is already user defined, like predefined. You can immediately use it. Okay, for whatever need, as per your need, you can take it. This is a typical logic diagram. This is a typical logic diagram. To my left or to your left, you will find the inputs, then some function blocks. Then to your right, the oval shape is the output. So whatever inputs you take. Then you put it into a software block where in case this input is high, what has to happen? This input is low, what has to happen? And the lines which are discontinuous, those represent digital signals. And the lines which are straight and continuous, they represent analog signals. So with this picture, I'm sure you're able to visualize a logic sheet as to how it will look like. Okay. So this is also a clearer picture. This is a block. This is maybe a motor control block. And this straight continuous lines are analog signals. This lines which have gaps are the digital signals, which will ultimately, these are all inputs. To the right of the block are the outputs. To the left of the block are the inputs. Okay. So with this, we go ahead from engineering tools. As I told you, after there are many other features, even international language support and many other things can be done through the engineering tools for a DCS. Okay. Now going ahead. As I told you, engineering tool is the human machine interface for a C&I engineer. Human system interface is the graphical interface for a operation engineer. So ultimately, if you don't make it understandable for a operation engineer, unless you put it into beautiful graphics and make them visually see what is happening, then there is no point in having a DCS. Because when a pump starts in the field, the pump, if it is green in color in the off condition, it has to immediately turn into red, or maybe it has to start rotating, so that the operation engineer easily visualizes saying, yeah, when I gave the command, this particular pump has started. So that way they have to understand. This is physically what we have done in our power plant also. Not only that, Sometimes the feedback comes up, but actually the pump has not started or motor has not started. So we also give current parameters. Once before the command was given, the current was 0. Now the current has raised, and the current also we put it in a graphical trend form where the current rises within a rectangle like this. So everything is visually very, very easily understandable. The human machine interface is very massive. It can have somewhere around 130,000 tags within one tag database. So imagine how many parameters we will be using in a power plant and how much we will be taking care of. So tags, each and every parameter, each and every input, each and every output is all called a parameter. Everything needs a separate tag. So we can have at least 65,000 Boolean and 65,000 non-Boolean tags within the human machine interface where we are using. In other DCS, maybe latest any other DCS would have come out, they may have better capabilities also. Okay. Then going ahead, in one HMI system, HMI is another application software. Okay, you can at least have 10,000 graphic pages. Hope you're able to imagine. The operation engineer seated in his computer, he is able to access at least the entire power plant in 10,000 graphic pages. In this graphics page, you are able to see the turbines, blades, and other things. I will be able to show you Nalco's some other graphic pages also as we go ahead. But then within a single computer, sitting in one single computer, he is able to navigate to so many pages, and the maximum capability of the HMI that we have got is at least 10,000 graphic pages. Okay, so it is very, very massive, and it is very, very useful also. And for every analog parameter or even for digital parameter, we are able to have trends. Trends are very, very useful. When imagine at this particular temperature, when the temperature goes more than 565, the turbine has to trip. Imagine the main steam temperature has to go more than 565, the turbine has to trip. Then the first point the operation engineers will say is, oh, it was not at all high and it has got tripped. So then as C and engineers, we will go and we will put the trend and we will show, see exactly at 565 only, your turbine has tripped. So once logic is set, we are not, logic is not a human being, or a DCS is not a human being to do any mistake. So please don't misunderstand the system. Maybe we have missed out. So human can create, when a human can make mistakes, but logics, once it is done, unless there is an input or output failure or there is a processor failure, logics never make any mistake. That is the advantage. Okay, that is the advantage of a HMI or a DCS system. Now in the HMI, as I told you, we were able to have 130,000 tags, and we were able to have 10,000 graphic pages. Now in a single page, in a single trend page, at least 60 trends you can see, 60 parameters trends you can see. Okay, these are all helpful when there is a lot of problem, maybe grid related problems, or when there is a total power failure in the Orissa grid. Then we will have to analyze so many parameters as to why it all happened. Okay, so in those times, these kinds of things are very, very useful, even for small issues inside the plant. When there is confusion between departments as to why this happened, whose area was at fault and all, it is very, very useful. So DCS gives us a lot of features like that. Now display builder is also another interesting, it is like it is an art. You can keep on beautifying your page by giving better. See how visually an operation engineer is able to see the chimney, he's able to see the turbine, he's able to see the pumps and motors and cooling towers, and how air flows, how water flows, how steam flows. Steam pipelines are in different color, water pipelines are in different color. So when you physically see a DCS human machine interface page, it is very interesting to find out almost everything. You are able to sit inside the control room and see. Okay, so now this architecture of the human machine interface is like this. This we have earlier also understood. Only thing, the HMI systems are seated in the LAN network, and it is all communicating to the servers, to the control network and the panels, and taking all these inputs. Okay. Now for the next 5 to 7 minutes, I'll be showing you some pictures of Nalco graphic pages where you will be able to see what it is. So now DCS in power plant, in case you are able to visualize, this is Nalco with all the 5 chimneys, and these chimneys are for twin units. So we are controlling at least 10 different power generating stations with dedicated distributed control systems for each unit. Okay. Now, in Nalco very especially, as I told you earlier, we are having the steam generation or boiler. Then we are having the TG, turbine generator or turbine controllers, and then the balance of plant. Okay, this is how we have distributed in Nalco. Then, as I earlier told you, this is how signals are being distributed. I'm skipping off this slide and the next slide because we have discussed it earlier. Okay, special signals also I have explained to you. Now, when it comes to the logics, this is something I want to explain to you. Imagine some parameter is very, very critical, which will cause the tripping of the turbine, or it will cause the tripping of the boiler. With one particular parameter or one particular field device, you cannot depend on it and you cannot trip it. Okay, because the transmitter which causes the tripping may be only 70,000 or 80,000, but the cost of one single tripping may be 7 to 8 lakhs. So what we normally do is, if there is a very critical parameter, we put in at least 3 transmitters for a single parameter. Imagine main steam temperature. At least 3 thermocouples we put. We take all the 3 thermocouples inputs to the control room, and then we have something called triple measurement scheme. Okay, when it is very critical, we go to the triple measurement scheme. When it is not very critical, but at critical, we go for a dual measurement scheme. And with this, what we are able to do is, unless it is 100% low or 100% high, and it is all voted by 3 different transmitters or 3 different equipments coming through 3 different wires, going into 3 different modules, then decided by 3 different logic pages. If necessary, put into 2 different processes. If all these things are true, you will just trip the turbine. Hope you are able to understand what I'm saying. If the parameter is very, very critical, just a minute. If the parameter is very critical and that will trip a turbine or a boiler, it needs veracity, like it has to be accurate. So the probability of one transmitter or one equipment or one field device failing may be there. But to make it 100% accurate, we install 3 different transmitters, carry the signals in 3 different wires or cables, coming to 3 different modules, which are maybe housed into 3 different controllers also, or panels also. So there is no point of error happening in a trip system. So these are all very, very important. Same way, logics of digital inputs also can be done like that. At least 2 out of 3. If 2 digital inputs are coming, then only it will trip. Like that we can do. Then first out logic, as I earlier told you, the sequence of events. This first out logic is very, very important. Whenever, imagine in a turbine's protection, at least we have 27 causes for which turbine can trip. And when turbine trips, at least 5 to 7 causes are displayed in the screen. Now the operation people and the C&I engineers, control and instrumentation engineers, will be worried which was the first. So this first out logic pages, graphical representations, will clearly say these are the 10 different causes which have come up. Of all these 10 causes, this was the first cause. So the first out or the first cause logic is very beautiful. It is designed in the logics in the engineering station. It is graphically visible in the HMI. Okay, so that way you can very easily find out the first out. Apart from that, any HTLT motors, bidirectional, unidirectional, then single coil solenoids, whatever device is in the field, accordingly you can go for different kinds of controls. So this is the typical index page of Nalco's DCS. Okay. We will have so many pages where operation engineers can immediately, by the click of a mouse, they can reach to that particular page. And one side you have the turbine, other side you have the boiler, and in between you have the balance of plant. Everything is available in one single page, or if necessary, even some more index pages can be designed. So typically in an Alco power station, we have 5 ball mills in the boiler. So all the mills are all visibly seen, their currents, their flow, airflow, their feeder speeds, and their on-off indication, whether it is rotating or no, everything is visible for the operation engineers. This is a typical graphic page of a turbine. Turbine will have so many bearings and all the bearing temperatures and expansions, vibrations, everything needs to be very closely monitored. So all those parameters are coming into the DCS and are all displayed to the operation engineers. In case of a value going above the alarm value, it will give an alarm. If it is going above the trip value, it will go for a trip. So this is a better page. See, as I told you, the pumps which are not running are in green color. The pumps which are running are in red color. And the valves which are open are in red color. So you will be able to visually see, okay, these are the pumps which are running. And whether if you have a doubt if the red indication is really running or no, there will be separate pages where you will be able to access the current of these pumps. So once current is there, you are almost damn sure that the pump is running. So this is the turbine page. TG, that is high pressure turbine, intermediate pressure turbine, low pressure turbine, and generator. All the parameters are visible. The oil lines, which line takes drain oil, which line takes the lubricant oil, which line takes the lifting oil. Everything is visible. What is the level of your main oil tank? What is the temperature of the lube oil temperature tank? At what parameter a pump has to start or stop? Everything is completely designed in the logics. In this page, you have the electro-hydraulic control station of turbine, where the turbine control valves opening. As I told you, graphically, you are able to visually see that it is 72.39. Though the digital value is shown below, graphically also it is visible that it is 72% open. So this HMI has got these kinds of features which are very, very interesting. Now, this is the single line diagram of a 220 kV switch yard. So this is also part of DCS in which all the colors can change, the main bus and how our CPP is giving power to smelter and to the grid. These are all things which we have analyzed. So additional benefits of DCS is life cycle optimization. There are a lot of decisions which you can take based on the history and data. As I told you, you can management can take decision whether fuel efficiency was there or no, whether we have been able to run the power plant in an optimized manner or no. Those things can be also possible. Another thing is optimized operation also. Whenever you find that there are excess wastage of water or air or coal, consumption of coal is more, those things, and even plant aging, how to do a residual life analysis. For all this, your DCS can help you. With this, I want to close my presentation. If you have any questions, we will be taking up for maybe next 10 to 14 minutes. Thank you all once again for this valuable opportunity.
Thank you, sir.
Excuse me, sir. This is Arya.
Thank you, sir.
I have a question, sir.
Yes, please.
That connection between what is the main difference between connection of a DCS, means of a HMI and a DCS? You told, sir, in HMI the connections are through LANs only. And what about DCS? How it is connected to the sensors and actuators? That's the question, sir.
Okay. So for that, we will go to the in this diagram we'll go. See, as I told you, the bottommost line, right? These are the field devices.
Correct.
All these devices are entering into a marshalling panel or a junction box, which is just a physical termination unit only. Any cable which is coming from the field is terminated into a marshalling or a relay panel. Okay. From there, again, cables are carrying those signals to the control room or into the DCS and into the modules through another field termination units. So wiring parts ends in the DCS nodes, which are having specific field termination units. Okay, wiring part means, what I mean is physical wires are going from the control room up to the field device through a marshalling or relay or junction box. Okay, why we are doing this is this every individual field equipment cannot have an individual cable up to the control room. So in a particular area, if there are 15 to 20 equipments, all those equipments are having short cables and they are coming to a junction box. And from one junction box, we have a big cable, which is maybe a 32 or 64 cores. It can carry 64 signals, or at least 32 signals at a time. It will bring it to the marshalling box. Okay. From there, you are again taking it to the DCS nodes. Now these modules, they are getting individual inputs in individual wires. Okay. Whether it is coming into a big sized cable which can carry many signals, or from an independent cable from the field, it is coming to the control room as a signal. As I told you, imagine now his question was how the field signal comes in and how it comes to the human machine interface. Now this field signal, imagine we have a pressure transmitter. This pressure transmitter will be requiring a power supply to power on. So power supply, that power supply is given by the DCS module. If it requires 24 volt DC, it will go from the DCS module through the same wires which are connected to the pressure transmitter. This pressure transmitter, once it is powered up and there is a process pressure, imagine it is of the range of 10 kg, 0 to 10 kg, and the actual process pressure is 5 kg. Okay. The output is given in terms of 4 to 20 milliampere. So ideally for 5 kg pressure, if it is 0 kg pressure, it would have shown 4 milliampere. For 10 kg pressure, it would have shown 20 milliampere. For 5 kg pressure, it will show 12 milliamperes. So 12 milliamperes will come to the control room to the particular IO module, not IO module, to the analog input module. Now the analog input module receives that current from those two wires in which it sent the power supply, and it is keeping that. Now there are as I told you earlier, there are modules which do the analog to digital conversion, and that digital conversion converts this analog current value into a value understandable by the DCS. Okay. And in the engineering station, you have typical function codes for receiving an input signal, analog input signal, make it into an analog output tag so that it can be visibly seen in the HMI server. As I told you, engineering stations, this control network, on top of the control network, both engineering stations and the HMI servers, they're all seated. So they are able to get all the data. Now the HMI, human machine interface, they are seated in this LAN network. Once it is available in the server, just as your Yahoo servers or Google servers, just once they are having everything, you are not able to edit any data, right? But you're able to access or visibly see any data. That's how the HMI works. Any data which is already brought into the DCS, which is understandable.
So HMI connection is from engineering station to the server only. And from server onwards, we are going by port to 20 communication to directly to the marshalling relay, and from there to the junction box, from there to the actuators, whatever the
actuators or fields or whatever, right? 4 to 20 in cases of analog.
You told one thing, sir, that ADC part. So where the ADC are placed means in the junction box or in the DCS nodes.
Inside the DCS nodes. Inside
and
the DCS.
Those digital signals are transferred through means of a LAN to engineering stations, right?
No. This control network. In the control network, all these things happens only to the operator workstation. That is the graphical HMI. For that reason only, we are using the LAN.
So, sir, what is the basic uses of ES of engineering station? Means they are using in control room. A separate part is there in a control room, and a separate part is there as the engineering station. So what is
in the engineering station? In the engineering station, we are having two important computers. One is the server and the engineering station. In the engineering station, inside the processor, whatever is already loaded, how will you come to know? So you need a interface, right? In fact, inside the processor, there are so many logic pages, or the entire project of Turbine is loaded into a single controller, which is inside the node. But what is inside, we don't know. So once you access with that particular application and open that particular project, exactly whatever is inside the processor is visible here also, in the engineering station also. Okay. Are you able to understand?
Yes, sir. Yeah, getting you.
So once you open any logical page, okay, this particular field signal or this particular actuator's position is coming into this DCS as this signal, 4 to 20 milliampere signal, and now presently it is 50% open. So everything is available in the engineering station. But for operation engineers to access the engineering station, understand the logics and all is not possible. So we are giving it to them in graphical representations. Alright, this you have started, this has happened. And permissives maybe in written word forms we are giving, so that operation engineers will be like laymen only. They can read and understand, they can see and visually control. Engineering station is where you will enter into the logics part of it. Operation engineers also need to understand the logics. But then for regular operation, if they are forced to sit and think and only operate, then it's not possible. They need to immediately take action. Okay.
Right, sir. So, sir, you were saying that from HMI, a bidirectional communication can be done from actuators to the through your DCS node to up to ES or up to HMI, and then from HMI through DCS nodes to the Marshall relay, and from there to the actuator. So a bidirectional communication, and the green lines are what you are showing there, the supervisory network, Ethernet and all. So that is connected to the server, and from the server through physical wires, we are connecting to the DCS nodes, that red lines. These red lines are in the form of digital signals, right, sir?
No. They are the control network.
They are the control. So which type of signal flowing in those red lines, those part that means through you in your figure, that CNET to the DCS nodes, those boxes, those black boxes.
They are packet data, maybe like the ring topology, how you transfer data, right? It's data.
Like HTTP or any protocol, we can go for that, right, sir?
Yeah. Depending on the service provider or
there, those
DCS
yellow
provider.
bidirectional communications, those are 420 communication, right, sir?
Not only 420. In case of analog, it's 420. In case of digital, it will be 24 volts or 0 volts, depending on what input it is. Okay, if it is analog, it is different.
So digital signals means you told, sir, the analog 4 to 20, digital 0 24 volts. So we are converting to digital in the relay part, in the Marshall relay part there also.
Yeah. No, we ideally imagine if I want to explain to you in the HMI, when an operation engineer is pressing the on button of a particular motor. Okay. Through LAN, the button, the soft button in the graphic page is pressed. That much only he does. He doesn't understand what is happening in all.
Correct.
So once he presses that particular button through the data, that particular button has got a tag, right? The particular tag which was in 0 state, when he pressed it, it has become 1 state. In the engineering station, if you are sitting, you will be able to understand that when he had not pressed it, it was in 0 state. Now it has become 1 state. Correct. This 1 state of that particular soft button means that this particular motor has to start. So in that case, that input button will be going into another software function block, which will give you an output, which will go to the field as a 24-volt DC.
Right. Okay. Got points. Now
again, in case in the field you are having a transmitter, it is coming into the control room. It is coming to the control room as a 420 milliampere. This 420 milliampere is made to a digital form of 0 to 100 kg pressure or whatever it is, and then graphically in the screen, either the operation engineer sees a 0 to 100% only. What happens within, he doesn't understand. Okay.
Yes, sir. So another question on the control part. Just now, the last, maybe the third last or the fourth last slide. That first communication means a trip occurs. Then why the trip occurs? That first it will go for the first variable, then the second variable, then the third variable or the fourth variable. So my question, if trip occurs, then automatically means. If the trip occurs, then the variable the for which the trip occurs, that cause will show in the HMI. Okay, that's a fine. But once trip occurs, the communication breaks down. Then how the second variable value will come? Means if the communication breakdown is there, no value of second variable will come on the display.
No. Communication.
What is the logic on that?
No. Trip. I mean, what I meant was the process trip of a turbine or the process trip of the boiler. Okay. Now
Right.
communication, there is no break in communication. This break of there is no physical breaking of wires or the red control network communication breakage or the LAN network breakage and all. If those things happen, that can also lead to a entire powerhouse tripping. That can also cause if there is a control network failure. And that is why we have
So
given
what
control
is the
network.
meaning of a digital tripping? What is the meaning of a digital tripping? Let's say we are showing for a watchdog. If watchdog is greater than 0.5, then we will trip the communication. Means we will switch off the switch. We will just
No,
off the switch.
we won't switch off a trip. For a turbine, tripping means you will be you will be cutting off all the steam input to the turbine. That is
Right.
called turbine trip.
Right.
So imagine lube oil pressure. Lube oil pressure means the oil which lubricates the turbine between the moving part and the static part. If there is no lubrication, turbine will get drastically damaged. Okay,
Correct.
heavily damaged. It can go to rubbing. It can cause fire. It can cause damage to the main shaft, which is a 150 crore equipment. So that
Yes,
is, you cannot imagine that to happen. So lube oil pressure low is being sensed by a pressure switch in the field.
Okay.
So in case there is a transmitter, that would have been an analog signal. In case there is a switch, it will be a digital signal.
Right.
So lube oil pressure low, less than 3.2 kg, instantaneously turbine has to trip. So what we do is, as I told you, because it is a trip signal, we will have at least 3 different pressure switches, and we will decide the trip by 2 out of 3. If 2 pressure transmit switches vote at the same time that it is pressure low, instantaneously we have to trip. That is the digital. That is the digital input. And when that trip means, what we do is we immediately stop all the control valves and stop valves of the turbine. We give a close command. Or if there is a common trip oil which can close off all these valves, we drain that oil. By draining that oil, everything closes.
Right.
So ideally, there is no breaking in the communication or control network. Imagine before this lube oil pressure low happened, the pump has tripped. Okay. Now, what has caused the lube oil pressure low? That you will not know. So in that case, the pump tripping would have come as the first input, followed by the lube oil pressure low. Then you will understand, the pump which has tripped first is the actual root cause of the tripping of the turbine. That is what I meant by first out logic or sequence of events logic. Okay.
Okay, so means my question was, if a closed loop control is going on, and the closed loop control means the tripping is coming, the tripping signal is coming through a single variable, and the tripping signal is generating a binary switch, a binary action like 1 0, 1 for trip or 0 for no trip. And for to cause one, there are multiple reasons, maybe 10 reasons or something. So if we are going for that 1 0 command, what you told right now, to operate that stop command and all, so to do on that, is it possible? Is it possible to go for a means what I want to say, that means that 10 sensor signals is coming to a single binary, is that 10 sensor signal is creating a single binary 1 0, and how to combine that to go for this first out, this logic what you told just discussed, how to combine that in a closed loop control, sir?
No. There are specific blocks, function blocks, which have the capability of stamping the time, right? So and normally all the trip signals don't enter into a single module also, because if it enters into a single module, failure of that particular module can create so many tripping causes, right? So it is all in different modules also, but all those modules are capable of time stamping. And
so time stamping is the key here.
Yeah. But not just the time stamping. As such, DCS will have a cycle time in which it will access the 0 and 1 state in a continuous mode, right? So whenever one has happened in any one place, whichever has happened first only, it will take first. And when you do the engineering logics, the block numbers should be engineered in such a way that whichever process has to be monitored first should be having lesser numbers, and as you go in the logics, it will go to the higher numbers. I hope I'm making sense to you. Block numbers. Block numbers are very, very important. We have made some mistakes by like that also. When block numbers were not given in the right fashion, without something's happening also, it can trip. Because something else was sensed in the previous cycle, now something else is sensed in the next cycle of the of the time cycle of the disease. Then there will be problems.
Yes, sir. Okay, sir. Thanks, sir. Thank you, sir. Thank you for the clarifications. Yeah.
Yes.
Thank you, sir, for your valuable ideas about DCS, which will help us to gain more knowledge about in this field. So without any further delay, now I present our final speaker of the day, Engineer Lalit Sankar Nayak, an eminent personality in the field of training, delivery, and technical service under process, automation, and machine engineering, having 13 years of experience. He is currently working as field service engineer in Tetra Pak India Private Limited, Pune. He completed his graduation in Electronics and Instrumentation Engineering from NIST Berhampur in the year 2006, followed by his master's degree in Instrumentation and Control Engineering from NITTTR in the year 2014. He started his professional career as a faculty in Roland Institute of Technology, Odisha, then joined Schneider Electric, Chennai as senior technical training instructor for a period of 4 years. After this many experience, he got associated with Tetra Pak India Private Limited, Pune till today, and currently he is the services engineer. So it gives us immense pleasure to have him among us. Now I call upon our guest Lalit sir to throw some words on this very interesting topic, application of DCS in automation industry. So sir, please.
Thank you very much. I hope my voice is audible and it might be with a lot of noise. And may I know, I mean, the host who has addressed myself?
Sir Swabhimani Sahu.
Sorry?
Swabhimani Sahu, sir.
Swabhimani. Thank you, Swabhimani, for the brief introduction. So I hope we are already delayed by 5 to 6 minutes. So I'll not take much of time. And at presently, I'm not able to make my laptop camera on because it is not accessible here. So I have connected through my mobile as well as the laptop. And because and if you can see right now, I'm at a customer site for some preventive maintenance activity. So there may be some network issues, and for that I'm really very sorry about it in advance if there is some network issue happening. Fine. So here I will share the content over on my laptop as well. So first, let me make sure that I'm able to visible to everyone.
Sir, I am unable to hear anything.
Yeah, I have muted myself. I hope right now I'm audible.
Yes, sir.
Okay. Is my screen is audible to everyone? Hello?
Yes, sir.
Yes, yes. Thank you very much.
Yes, scripts are clear.
Yeah. I hope before this we had a seminar with one of our chief speaker, Mr. John, and I was going through for a few of his topics, and probably he was talking a lot about a pure application of DCS in a particularly for a boiler application, and you were in a discussion how the tripping happens and all those details. So from that content, I have understood what exactly there are some gaps. Maybe I can address it with my experience. This will be definitely to addition to Mr. John's content. So let me start with my topic here. So here I am going to discuss more about a particular DC system that is called as Foxboro. So Foxboro DC system, which is right now owned by Schneider Electric. So this DC system is quite older, same with Honeywell, and this is one of the most widely used DCS system in the industry, and the install bases are with refineries like Reliance Industries, then PPCL, IOCL, and also globally in the Middle East, it has a lot of footprint like with the Kuwait Oil Company, Abu Dhabi Gas, and Kuwait Natural Oil Corporation, KNPC. Not only with refinery, also it has a lot of footprint with power plant like NTPC and many Coast Gujarat Power Limited, that is by Tata, which is mostly located in the coastal Gujarat. Then many of these state governing plant like Rajasthan Rajya Vidyut Utpadan Nigam Limited. So all such footprints are there with Foxboro DCS system. So here, of course, I mean, maybe the speakers who have spoken about from Nalco, they might have talked about some particular DCS system which has been used in their plant. So here I'm going to discuss the same DCS system only, but with a, from Foxboro point of view. But I just want to mention here, if it is any DCS, whether it is from ABB, it is from Emerson, it is from Foxboro or Honeywell, overall the architecture of DCS and the networking concept for DCS, it always remains the same. From product to product, the hardware design difference, and you will find some additional features. It is just like, to give a layman example, it is just like you are buying a car. So you're buying a car means you're buying a car, whether it is from Volkswagen, it is from Fiat, or it is from Skoda. Ultimately, the purpose is same. You have a steering, you have accelerator, you have a gear, and you will use it for a commute purpose. So the same way, I mean, the hardware, whatever use, the structure of hardware, the networking concept, everywhere it is same. So the important thing here it is that what we need to understand, I mean, as a beginner, whoever is learning this particular technology or concept, in my view, the most important thing is that what you need to understand is how exactly a DCS system integrates with a real process. So right now, I mean, in the previous seminar, you were discussing about a boiler where you have couple of a tripping concept where where Mr. John, he was talking about a particular pressure sensor, which is a very critical one, for which they cannot rely on a single transmitter. So for that, they have 3 transmitters, so which has a logic of 2 out of 3. So out of 3, if 2 transmitters are saying, no, the pressure is low, so the value will be accepted as true. And based on that, the whole process or the whole system will trigger. That is something, a real application. So here what we need to understand, or from Foxboro point of view, what I'm going to explain is that right now on our screen we can see there is a tank is there which is filled with water or any liquid. So on this tank, if you can see on the left hand side, we have a pump, and the pump right now, then it is followed by a level transmitter. Okay, and in this tank we have an outflow as well. So here the purpose behind this particular example is that we want to control the level on this particular tank. So when I'm saying controlling, so controlling basically when it comes to industry, basically it is categorized into two different types. One is continuous control and another is purely, we can say, discrete control system. So when I say continuous control system, so there the controlling will be continuous, means the control output will be continuous. It will be like, okay, you can say analog output. Let us say if I am operating one particular valve, so I will not be operating as on or off. So there I will be operating at 10%, 20%, 30%, 40%, 50%. That will be called as continuous control output. But if I am simply making the valve as on and off, so that will be called as discrete control. So from your basic studies from the engineering subjects, I think where you have discussed, or you might have studied in the process control and its applications. So there you might have studied that a discrete control always not able to fulfill our purpose. Like in this case, right now on this particular level tank, I want to maintain what particular level exactly, right? Let us say this level, I can change it from 0 to 100 feet, and I want to maintain the level exactly at 75 feet. If I want to do so, so definitely a discrete control loop will not be going to help me. So on that case, we use the continuous control loop. So in a continuous control loop, the most common thing what we use is a PID application, where we have proportional, integral, and derivative, these three different controllers. So if you see in this particular example, so how we can achieve this continuous control to maintain the level in this particular tank. So that is my intention over here. So here, if you see, the first thing what we have here is the field bus modules, or which we call as the input IO cards. So the purpose of this IO cards, or in the term of Foxboro Dc System, we call it as FBM, or we call it as the field bus modules. So these field bus modules, they are basically responsible to send or receive signal from the field. So right now, if you can see here, this field bus module are communicating with this pump, they are communicating with this transmitter, and also the field bus modules are communicating with a PLC. If there is a separate PLC in the DC's architecture, so they can also communicate with it. So ultimately, the field bus module, it converts the field signal into DCS signal. So here, in terms of Foxboro DCS system, the DCS signal is called as IA signal, or intelligent automation signal, because Foxboro DCS has defined their DCS system as the IA series. They call it as intelligent automation series. So here, ultimately, this field bus module, they convert the IA signal for the field use. It means if a DCS is giving an output signal for a particular valve to open 10%, 20%, 30%, so that will be, the DCS will be providing the IA signal. IA signal means it's nothing, just a purely digital signal. But of course, based on a digital signal, we cannot operate a valve, or we cannot operate definitely to a form of analog signal, which we commonly as a field. So the purpose of this field bus module, in one way, they transfer the signal from the DCS system to the field. On the other way, they receive the signal from various transmitters. The pressure, the different type of transmitter, maybe it is pressure, flow, and not only just different measuring type of transmitter, also different prototype or protocol of transmitters. Like in a field, we may have a transmitter of heart, or we may have field bus transmitters. We have Profibus. So these different transmitters, they ultimately do the same thing. The purpose of this transmitter to sense the signal, but there the communication protocol is different. So right now, in the field of DCS, or in the process application, basically, if I'm talking about the refineries or in the power plant, we do not use simple transmitters. Now it is a generation of using smart transmitters. So the transmitters are smart. So these smart transmitters, they need a communication protocol. So for that, either they can use HART, they can use Profibus, or they can use field bus. So if there are different type of transmitters are there, so definitely you need dedicated field bus modules to communicate with such type of different transmitters. Like to communicate with a HART transmitter, you need a HART module. To communicate with a Profibus transmitter, you need a Profibus module. So it's in this way. I hope I am audible to everyone.
Yes, sir.
Yes, sir.
So thank you. So here, just please let me know if I'm not audible or because I have a lot of noise around me.
Yes, sir, you are audible.
Yeah. Okay. Thank you very much. So the first thing what we had is the field bus module, as I have mentioned. So after the field bus module, the next important thing what we have is the control processors. The control processor is nothing, just this is the brain of the DCS system. Okay, this is ultimately do all the calculation. Okay, what exactly we need. So as I have said you that to have a continuous control, we need a PID loop. Okay, so we need a PID algorithms. So all these algorithms will be residing inside the memory of this control processor. So ultimately, the control processor will be executing this PID algorithm to generate the necessary output. So if you can see here from this field bus module, this level transmitter is providing the signal to this field bus module, which is a purely analog signal. And this analog signal is converted into digital, or in terms of Foxboro Dc system, I can say IA signal. And that IA signal comes to the processor. So here the processor receives this input signal in the form of a digital. And inside the processor, we have developed a logic or a program in which we have defined a control loop where we have an input block, we will have a PID block, and we will have an output block. The input block will provide this digital input, what it has received from the field, and the input will be given to the PID. And the PID will then execute the PID algorithm. And that execution purely depends on the three values what you have studied in your book, that is proportional, derivative, and integral, and what it is, PID, what it stands for. Please tell me something. I want to know from you also what this PID stands for. Yes. Any of the participants, please let me know. I mean, not. Please tell me what you have, what understanding you have about PID, that is proportional, integral, and derivative control system, or why we use PID.
Sir, can you please repeat once again?
My question is that please tell me what is the purpose of PID.
Sir,
Sir, that is proportional integral derivative controller, I think. Am I right?
Yes, correct. But why we use it? What is the purpose of a PID?
Yes, sir, because as far as I am an academician, so what I understand that, sir, please, as I understand that PID is just to improve the efficiency, to reduce the steady state error, whatever I learn in theory. Am I right? Hello.
Yes, I am asking about the theory only. Go ahead. No problem. You are right. Go ahead. Please.
To increase the efficiency, basically.
Okay. So how it improves the efficiency? What exactly it does? Why it is called as proportional? Why it is called as integral? Why it is the name that is called as derivative? And how they are different from each other?
Yes, sir. Because there are three different sections. For example,
okay.
If I talk about a cloth industry, for example.
Okay.
Hello?
Yes,
sir. If I talk about the cloth industry, for example, then in cloth industry there are different sections. For example, there is particular knitting section, cutting section, coloring section, dyeing section, process house, right? So different kind of sections, whenever together held, there as a output of that complete process will be the output of that industry. That is a perfect shooting or shirting, right?
Okay.
So similar to that, there is a word proportional, integral, and derivative. These three kind of things are held together to improve the efficiency. For proportional, integral means just the output is the integration of that input, and in derivative, the output is just the derivative of the input in a very simple language. But as I learned this in control system subject, just the theory, the block representations and because of that block representations, we will find out the transfer function that will show the that damping will be increases, the frequency will be increasing, efficiency is definitely increases. Just I know this thing, nothing else.
No problem. What's your good name?
So my name is Rakesh Jain.
Okay, Rakesh, I'm sorry to say that the concept what you have or what you have understood, that is not exactly what a PID does. Okay,
Okay, sir.
so no problem, no problem. I'm really happy that you have made an attempt. But let me put it, or let me explain with some particular example. Okay, see, every control loop, it has some error. Am I right? Do you agree with me? Like if I want to
Yes, sir.
control a level of a tank, so definitely there will be some error. So what do you mean by a error? A error is nothing, just the difference of the value I want to maintain and the real value. Like for example, in this particular tank, I want to maintain the level of speed of 75, but with lot of effort, I am able to maintain the level at 79 or 78. So there is an error of 3%, right? So that is called as the error. So basically,
Yes, sir.
nobody likes error. Okay, so our intention here is to reduce the error as much as possible, right? So with the help of a discrete control, I can maintain the level, but I cannot reduce the error. With discrete control system, I may able to maintain the level from 65 to 85. But if I want to exactly maintain at 75, discrete control will not help. Fine. So now what do you have? The next thing is that I need a analog control. Okay. So when I am saying continuous control or analog control, so there the PID comes into picture. Okay. So first you need to understand that why this whole world is using PID, because we want highly precise control. We do not want any error. If I want to maintain at 75, so for me the acceptable range is from 74.5 to 75.5. That is acceptable for me, but it should not be like 70 to 80, right? So my precise, but I mean, I want to maintain the level at a precise value. So for that, you need a very intelligent control. So for that, we use the PID. That is the basic purpose here. Now, what a PID does, what extra thing it has. So in PID, as you have mentioned, it has three different control mechanisms. One is proportional, another is integral, and the third is derivative. Now, these three different control mechanisms, they work togetherly to ensure the optimum performance. So how they ensure? The first thing is that proportional control. So in case of a proportional control, the proportional action is directly proportional to the error. It means if the error goes high, the output also will go high. If the error comes down, the output also comes down. But single or by alone a proportional control, you will not be able to achieve the output of a control loop. Okay, it means, for example, if I'm saying here with the level tag, so if the level goes above 80, it will try to close the valve. If the level goes down, it will try to open the valve in this way. So here, the controller output or the control loop output will be very much oscillation. It means the complete waveform, if we will track on an oscilloscope, you will find it's a kind of a sine wave. But that is not desirable for me. So there what I want, I will add integral. So in case of an integration, it will ultimately integrate the error. So to understand a simple mathematical way, if you do some integration of any function, the value of that particular function value will come down. So the same way also here also it works on a basic math. So the error, if you keep on integrating, the error will slowly, it will come down. So now here one more very important factor is that if you use an integral action, it will take a lot of time to bring the error close to the set point. Okay, or the error to come down, it will take a lot of time. So we do not have that much of time, right? Let us say if you want to maintain a temperature inside a boiler, or if you want to maintain a temperature in a tank, so you cannot wait for 1 hour, 2 hours, right? So you need it to bring it to the set point as early as possible. So integral action will have a very long time of response. So proportional plus integral, of course, it is good, but they do not completely fulfill our purpose. Why they do not fulfill? Let us say with proportional integral, you are able to control, but suddenly the error goes beyond a very, very high limit. Like, if you find a surge in the error curve, so at that point, the proportional and the integral action will not able to help. So at that time, you need a derivative control. So the derivative control will really help you whenever there is some surge in the error. So to understand it in a very again in a layman way, I can say, let us say, if if any human being, if they do not feel good, like let us say one night one guy, he had his dinner and he went to sleep, and immediately he got a high fever, immediately. Okay, and the fever is going 102 or 103. So at that point of time, just drinking a hot water or just covering with a blanket will not help you, right? You need a paracetamol. Okay, immediately you take the paracetamol. So the paracetamol will be able to bring your temperature down, but it cannot kill the virus what it has really caused the fever for you. So exactly in the same way, even if you go to sometime whenever we get high fever, if you go to the doctor, they will give immediately one injection that will bring our temperature down. So derivative control is exactly something like that. Okay, if the error is very, very high, the derivative control will try to bring it down as much as possible. And once the error comes down, then the proportional integral will come into picture. And from that point, they will take over and they will bring the error value more down, or they will bring it to or near to the value 0. So that is how a P plus I plus D, they all three, when they work together, they really fulfill our purpose, or they really give us a better performance in case of a continuous control loop. So in case of this PID, okay, so to this proportional integral and derivative controller to act as per the calculation or as per the formula, they have three constant factors, which we'll call as the proportional constant, integral constant, and derivative constant, right? So based on these three values, the PID output will vary. So they are ultimately the tuning parameters, right? So this proportional, integral, and derivative constant value, they may not be same for every control loop. Based on different control loop, these values will be changed. So as a process engineer or as an automation engineer, you need to tune it. So as much as good you are with the usage of PID, you will be able to tune the loop, or you will be able to bring the value too near to the set point faster. So that's ultimately your skill. So you have these three weapons with you, P, I, and D, and by using these three parameters, you can really make miracles. So that's how a complete process system works. So here, as we have discussed, inside this control processor, we have some inbuilt PID blocks. They are called as the algorithm. So in this algorithm, you can, or the engineer or the developer, they can really change these values, the proportional constant, integral constant, and the derivative constant values. Okay, so based on these constants, the constant value, the algorithm will give the output, and the output will ultimately go to the field bus module, and this field bus module will convert the IA signal into analog signal form, and then it will go to the field. Fine. So till here, we have a processor, and it is communicating with some field bus module, and the field bus modules are communicating with the field device. But in case of a DC system, this process automation, it doesn't end here. It has another side, or the coin has another face. So what is that face? The face is where you will be able to see the whole thing on a supervision system, or you need a completely supervision of control, or you want to see what exactly happening in the field. Right. So for like in case of a refinery, or in case of a boiler, or in case of a power plant, the complete control system is distributed across the whole plant area. Right. So you will not be able to commute everywhere. That what is happening in this area, or what is happening in the boiler, what is happening inside the turbine room, or what is happening in the chiller. You cannot go everywhere. So you need to sit at one place, which you call as a control room, and from there you want to see everything. So that your DCS system will fulfill. So how it fulfills here? So if you see on my slide or on my screen here, so the control processor, one side it is communicating with the field bus module, on the other side it communicates with a DCS switch network. So the processor is connected to the switch, and from this switch, different type of workstations are connected. So if you see here, some workstations are called as application workstation, some workstations are called as the server. So based on the DCS software installation purpose, we have different type of workstations. So what is the purpose of different workstations, that we will discuss in a later stage. But right now, what you just need to know that from these particular workstations, an engineer can do some changes to the logic, an operator can operate the plant. Okay, one plant manager, he can extract some data for the purpose of some analysis. Like in the previous slide, in the previous topic, we were talking something about sequence of event, the data of SOE, or in a DCS we have something called a historian. So you can take history and data from these workstations. So there are a lot of n number of applications are there from the DCS system, and all those applications are installed on this workstation, and different user, whether he is a manager, he is an operator, he is a maintenance engineer, he's an electrician, or he's a technical engineer. Based on their different requirements, they can access these workstations as per their needs. So ultimately, a DCS system, it has two different ways. In one way, it completely update all these workstations who are there in the network, all the real-time values. Okay, so in case of your industrial instrumentation, when you study in your theory, there when you will talk something, you will study something about real-time data. So this is real-time data. A DCS system is able to provide you a real-time data. That what exactly is the tank level right now. To control the level in the tank, you have a valve. Okay, so that valve, how much it is, how much percentage it has opened now, what the transmitter value, what exactly it is showing. Okay, how much is the level in the tank. So all these informations you can see on the DCS operator screen. Okay, or on a DCS system, whatever applications workstations you have, there you have an operator window, and on the operator screen you can see all these values. This is a basic architecture of any DCS system. If it is of Foxboro, if it is of Honeywell, Emerson, Yokogawa, all system will have this architecture. Now here there is another. Here there is one catch is there. If you can see, all of you in my figure, in my slide, on the control processor, you have two blue color of modules are there. Okay, so they are actually two processors. Okay, one is primary, another is secondary. Okay, so this particular feature is available with most of the DCS system, but yes, this is one of a very common feature with Foxboro DC system or with Honeywell or Emerson. So here what happens, you have two control processors. So in any case, if one control processor fails, the complete control will immediately switch over to the secondary control, so that you will not have any loss of communication, okay, on the field side, neither on the control room side. Okay, you will not feel any glitch. I can say this transfer or this takeover is in milliseconds. Okay, this really doesn't make any difference, neither on the field control or neither on the DCS control in the control room. So this is called as redundant control system, or they are redundant to each other. If the primary fails, the secondary will take over. And in this case, let us say if the primary controller fails and the secondary has taken over, so what is our next target? That we need to replace that control. So here in this case of, or in case of Foxboro DC system, it is simply plug and play. You can remove the primary controller, bring a new controller from the spare or from the stock, simply plug it. It will, the second or the neighboring controller will share all the data with the new controller, and again they will start working together. Okay, so here we call them as a married processor or couple of, they are coupled. It is just like, you can say they are attached to with each other. Whenever one controller fails, the other one take over, and whenever we replace the faulty controller with a new one, the existing controller immediately hand over or immediately share all the data, whatever it has, so that in future, if that secondary controller fails, again the primary controller will take over all the responsibility. So that is how it works in case of a Foxboro IADC system. I hope my presentation is making some sense to giving you a enlightening on this system. And if you have any questions, please let me know.
So one question.
Yes.
That field bus communication is in the form of what is the mode of communication in the field bus?
Okay. Here, the field bus model, as I have mentioned before, it depends on the protocol what you have on the field side. Like if you are using a transmitter which is a HART module or a HART transmitter, then you will have a HART module. If it is a purely switch, like if I say, if you say it is purely digital output, okay, let us say it's a pressure limit switch. So in case of a limit switch, you simply need a digital output or digital input output module, okay, so or a digital input module. So simply the limit switch will provide either 24 volt or it will provide a 0 volt. So in that case, you will have a digital input module. If you are providing the output to a pump, so simply to make it on or off, in that case, you will have a digital output module, right? Then next, also we have basic analog input and analog output modules. In case of analog input module, the field transmitter will provide in the signal in a range of 4 to 20 milliampere. In that case, the analog input module will convert this 4 to 20 milliampere into some count, okay, and that count is nothing just a range of data value in form of digital, okay. So those count varies from system to system. In case of Foxboro Dc system, this count it varies from 0 to 32,768, right? So based on the different system, these counts are designed or it is calculated. So ultimately, here is the point is that they ultimately transmit the analog signal value what comes from the field into form of a digital, and that value goes to the control processor. Similar, if there is a HART transmitter, okay, so when I am saying HART transmitter, field bus transmitter, or Profibus transmitter, maybe these terms are maybe new to you, but let me tell you something, a basic concept about this different type of transmitter or why they called as the smart transmitters. Because these transmitters are smart. Why they are smart? Because if it is required, these transmitters, they can diagnose themselves, right? Right now, if let us say if you are using one sensor, okay, you have one sensor in your automobile or in your vehicle. So if the sensor starts malfunctioning, or if the sensor is not working properly, so how you are going to do the diagnosis? What you will understand, because if the door sensor is not working, then your car will not, you will not be able to do the ignite your engine. So from there you will able, you have to check on your display panel that the door is not closed. So here, if the sensor fails, the sensor doesn't have the capacity to declare himself that I am faulty. So that is a basic behavior of a sensor. But when it comes to smart transmitters, they are able to diagnose this themselves easily. They can do their self-diagnosis. They can declare themselves, yes, I am able to work or I am not able to work. So if I am not able to work, it becomes or it makes the life of the engineers very, very easy. Let's say there are a lot of transmitters. Okay, in a plant.
So one interruption, sir.
Yes.
So, sir, a transmitter to decide to become smart, to decide whether the sensor is have a fault or something, it need a processor.
Yes.
Similar. So where the processor is there in the transmitter means either in the control processor or in the field bus model where
No.
it is.
See, what is your good name?
Myself, Arya, sir.
Arya.
Yeah.
See, this processor, what you're talking about, they are not part of the DC system. They are part of the smart transmitter itself.
So where are you placing that? Where are you installing that smart transmitter?
This is a complete one single module. It comes as a single device.
Okay.
And this device is supplied by any vendor. Maybe it is made of Honeywell, it is made of Foxboro or ABB. There are a lot of players out there in the market. So they provide this.
No, sir. My question is, where are you placing it in this communication diagram? What you are showing?
Yes.
Where is the place? Where is the place? It's
where
here.
where I am making my cursor. That is the transmitter place. So then you can have a smart
at the bulb, sir.
No, on the right side of the screen.
Okay. Your mouse cursor is there. Okay. Yeah.
Okay. So there you can have a simple analog transmitter, or you may have a smart transmitter. So if the smart transmitter is enabled with HART protocol, then you need a HART module here to communicate. If the smart transmitter is enabled with Profibus, then you need a Profibus module here. In this way, I hope I have made it clear.
Completely clear, sir. Yes, sir. Thank you.
Thank you. So the first thing what we have discussed over here is that how a Foxboro DC system hardware, or in general any DC system hardware, how exactly they interact with a control system or a control loop. Okay. Now, on this screen, you are able to see only one tank, where you have one transmitter, you have one pump, you have one input valve. Okay, the valve which will function. But in an actual plant, you will be having thousands of transmitters, thousands of pumps, thousands of valves, because they will be responsible for maintaining or controlling level, temperature, flow, a lot of things will be there. So when it comes to huge number of input and output field devices, at that time, you need one particular system which will be able to scatter himself in the whole network and to collect all the data, bring it to the control room or bring it to the server room and do the necessary execution and send it back to the field. And there your DCS system comes into picture. That's why we call it as a distributed control system, because the whole control system is able to distribute himself in the whole plant. So in this case of Foxboro, this is one control processor. So here, this control processor capacity is not depending upon number of inputs or number of outputs. Here, this control processor capacity depends how many number of blocks it can keep inside its memory. So when I am saying blocks, it indicates that a block may be to read an input, a block may be to send an output value, or a block may be what it is required to do a calculation. Maybe it is a PID block, it is some separate algorithm block, it is a timer block, it is a counter block. So based on this number of blocks, this control processor capacity is defined. So one control processor, definitely it is not able to control one whole plant. So when it comes to a DCS system, so you will have more than one controller. So in case of a Foxboro DCS system, we can have 1920 systems in one network. So when I am saying 1920, so this 1920, this includes the control processors, the workstations, and the switches. So from this, you can really imagine that how big could be a DCS network, one DCS network. Okay. So in case of Foxboro DCS system, this has a capacity that it can have 1920 devices or stations. We also call them stations in a single network. So where the station is defined as maybe the control processor, maybe the switch, or maybe the workstations, anything. Okay. So usually when if I will mention you with some example, the biggest installation with the Foxboro DC system is the Reliance Refinery, which is located in Jamnagar. So there we have 3 phases of refinery: the phase 1, phase 2, phase 3. So far, when I was working with Reliance, the refinery 1 and the refinery 2, they were using full phase of the Foxboro DC system. It means In the phase 1, the complete network was having more than 1700 workstations. It means the network was very, very huge. And here one more thing is that one DCS network, again, it can communicate with other DCS network. That is also possible. For that also we have some separate modules. By using those modules, one DCS network can send some signal to the another DCS. That is also possible. Okay, this is just for your information. We need not to go much deep into that area. So here, if I'm coming to one single DCS network, where I have mentioned, as we have discussed, that it can support up to 1920 workstations or elements in a single network. And the next, coming to a DCS network architecture, I hope you have already discussed about it with the previous seminar topic where Mr. John, he was talking about the architecture. So inside architecture, what exactly a DCS does. So my next content, I will be shifting to the software part of a DCS. So far we have discussed something about the hardware. Now next I will move it to the software, because the software also they plays a very, very important role in case of a DCS system. Now, being an instrumentation engineer or being into the field of instrumentation, so here I would like to mention is that working on a DCS system is not just working in a purely core sector. If you want to work on a DCS system, you should have a basic concept about the hardware. Okay, hardware in the sense, what is analog processing, what is digital processing, what is analog signal, what is discrete signal, what are the different type of control loops what we have. Okay, and also if any one of you, if you have studied some of these papers, I don't remember what comes under BPUT because it is more than now 15 years. There are some subjects where you have or you might have studied about feed forward control, right? Feedback control, and different type of control actions or control loops are there. So these control loops or these control designs are always used in different plants. Okay, so to understand or to work on a DCS system, that becomes your core side. On the other side, you need to understand what is a network. Okay, the basic networking concepts. You need to be very, very strong on that. It means the 7 layer of ISO models. Okay, then what is data transmission in the form of packets. And here, in this case of Foxboro Dc system, if you have seen in this network, you have the switches. Okay, so my dear friends, these switches are not the switches what you use in your house. They are managed switches. You need to program them. Okay, so why it is programmed? The first purpose to make them manage or program is the first purpose is security. They will be secure. Each Ethernet port of this particular switch, they can be locked with the dedicated IP address. So if any device with that particular IP address is connected, then only that port will work. So you can do the programming or you can decide the port IP addresses by making these switches as managed. So to do all those things, you need to be very, very clear about the networking concepts where you need to address the IP, you need to mention the subnet masking, you need to define the switch configuration. So that comes the networking concept. Then the next thing is that it comes to the workstations. So these workstations, they need to install with a lot of softwares. So DCS is not just using the software. When you are going to develop a DCS system, ultimately the DCS engineer is going to install all the software. So these softwares is not just a simple exe file. They will be coming with a lot of SQL database installation, then Visual Studio installation, and then coming to the DCS installation. And depending upon the different DCS system, the installation procedures will be different. So all the software will not be installed on a simple processor system. Some software will be installed on the server. Some software will be installed on a simple PC. And some of the softwares need some prerequisites before installing. So all these concepts comes in picture. So my point is here is that when you're working on a DCS, you need to be very, very good on the hardware part, that is the core, at the same time also the software. Okay, so don't think that working on a DCS is purely like a core. No, if I mean in my experience, if I say core, it means a electrical engineer or a mechanical engineer or a civil engineer. But when I say instrumentation engineer, he's not purely into code. He is integrated. The instrumentation engineer, he need to understand the software. He need to understand the programming. He need to understand. He need to have some programming skill. He need to understand the basic electrical concept. He also need to understand the robotics or the electromechanical concepts. Everything is required for you. And this is the best example for that. So here, so that's why the next topic what I have planned for you here is the software part. So in case of a software part, here we'll discuss what are the different type of software we usually use in case of a DCS. So of course here I will talk about the software which is used by Foxboro DCS, but as I have mentioned earlier, in general, most of the DCS systems, they have the same way of installing the software or using the software. So I hope my screen is visible to everyone.
Yes, sir.
So so on this particular slide, we will see what are the different type of softwares or software functions we need to understand in case of a DC. So on the top, as it is mentioned, Foxboro Evo control software. So this particular completely slide what I'm using, that is for the Foxboro DC system, but it's a generalized thing. So to understand this, if you can see on the lowest category or at the completely lower level where you have the process or the process plant, okay, it may be a refinery or it may be a power plant. And on top of process, you have the IO control and the alarming. So they are responsible to do the input-output communication and to do the ultimate control. Fine. So IO control is able to control the complete process, or they are ultimately running the whole plant. The next thing is that you need to supervise, you need to have visualization, you need to have history, you need to manage your whole plant. So for that, we need different applications. So let us see what are the different applications what we have here. So first is the application software. The application software is nothing just there where you ultimately develop the whole application. It means the programming, the coding, or developing the logic. So that is the application software. Then the next thing what we have, the historization. So historization, which will be ultimately logging the history data. So what is history data? It means what has happened in the whole past. Okay, right? If you are running one plant or if you are controlling some process, all your history data is going to help you in many different ways. One of the purpose of logging a history data is to do root cause analysis. It means if something has happened in the plant, if something abnormality has happened, and you want to know why it has happened, so for that you need to have a log, and that is ultimately restored or that is stored or that is captured by the historian application. So in case of Foxboro DC system, this historian application ultimately this pulls data from the server. Okay, So whatever the data it is collecting from the process, it is giving to the server. And whenever the client, it means you or the operators or the plant engineers, they want to see the data, they will access this client machine. And in the client machine, you will having a client application. This application will be pulling the data from the server and it will display you. Maybe in the form of a graph, maybe in the form of a trend, whatever it is. Okay. Then the next application what you have, that is called as visualization. What is visualization? Ultimately, the operator who is sitting in the control room and he is seeing everything in front of him, that is ultimately called as the visualization. Okay. So here, if you see on top of this visualization, you have there are pictures of a control room. So ultimately, in the visualization, the operator will able to see the performance or behavior of the whole plant, that how it is actually working. And they will be able to give the operator input from the operator screen or from the operator workstation. So the two major things what you need here, or that is must. One is the application workstation, another is the operator workstation. They are must. Historian, sequence of events, okay, plant management system, material management system, MES, okay, boiler management system, BAMS, all these things are optional. But yes, you can integrate them with a DC. And that integration ultimately nothing called as the plant management. Okay, so in a plant, you just don't have to, or the only purpose is not to have a production or to run the whole plant. At the same time, also you need to maintain your inventory. Okay, you need to maintain your supply chain system, or in a plant you may have your own ERP also, like SAP or Microsoft Azure or something by Oracle. Okay, so this ERP will be ultimately pulling the data from the DC system. Okay, so if the DC, whatever the raw material is available with the plant, based on that the DC system is controlling the whole plant. So the ERP system will be pulling the data from the DCS, that what exactly is the output of the whole plant. So that also can be shared with the plant management system. So for those things, ultimately the information will be shared by the Foxboro DC software, which is installed on a different workstations. So these all are the basic software functional areas where you need to before handing over the complete DCS project to any customer, all these workstations are installed as per the requirement. Okay, so this installing of these workstations also comes in the scope of a DCS engineer. Keep it in the mind. Never think that installing a software is not a job of instrumentation engineer, it is a IT work. No. In case of DCS, you only have to install and you have to ensure that all the functionality of the software is working as per requirement. Okay. Now, so the which workstations you will be installing first? The workstations on which you are going to develop the application. Okay. So the workstations on which you are going to develop the application, those workstations will be installed first. Now, here one more catch is there. So these workstations, what happens? They are going to be supplied to the customer. Okay. So these all are the new workstations. So let us say there is one new DCS project has been given to Foxboro company, maybe by NTPC. So NTPC has given a project to Foxboro, and now Foxboro is now going to develop the DCS project. So to develop the DCS or to make a new project, the first thing what you need is that you need all this hardware. So hardware will be ordered from the factory. So by the time the hardware arrives, you can't wait, because it will take 30 to 40 days of time. Okay. So meantime, you need, or the complete team, they have to start work on the engineering. So for that, they need actual workstation, because these workstations is not just like a normal PC, because they are high-end configuration computers. Okay, maybe it is a server or maybe it is a simple workstation. So in this case, what we do, the virtualization, the concept of virtualization come into picture. Any one of you have any idea about virtualization or VMware or VM image? Hello. Does anyone knows anything about virtualization or virtual environment? Okay, so if nobody's replying anything, shall I make it as a, shall I consider it as a no? Or if anyone has any idea, please share with me. Don't hesitate. What is virtualization? We use a lot of virtualization concept right now in the market. It's everywhere. Yes.
Hello.
Hello.
I think virtualization is where you're not able to have the actual hardware to do it, then you work in a virtual environment without connecting in a direct base with the hardware. You can have a virtual environment and work with the virtual environment and then implement in the hardware later.
Okay. What's your good name?
I'm Leo, Leo.
Leo, you are absolutely right. What you have mentioned, that is absolutely correct. So that is the purpose of a virtualization, that where you do not need to have the actual hardware. Okay. Like, for example, I'm using right now my laptop. So let's say I have done some project work on my laptop, maybe on some coding, or I have a lot of software I have installed on my laptop. And I need to carry all these things to another remote area or to a different location. But I don't want to carry my laptop because my laptop, I cannot carry, maybe for some any reason. So in that case, what I can do, I can create a virtual image of my laptop. So the size of the image will be the size of the data what it is there in my laptop, the read-only memory and also the RAM, everything. Based on this size of my laptop memory, the VM image will have the same size of file. So my laptop memory, if it is of 60-70 GB, the VM image size also will become 60-70 GB. Now that virtual image, I can simply copy on a hard disk and I can move anywhere. Let's say I move to Bhubaneswar, and right now I'm in Bangalore, I'm in Bangalore or Pune, and I have taken a VM image and I moved to Bhubaneswar. And there I have opened one workstation in your lab. And in that workstation, I need to install one software that is called as VMware. Okay, that's a openware software for few of the versions or for 1 month trial. So I will simply open the VMware software, and in that VMware software, I will open my VM image. So when I open my VM image, ultimately it will open the operating system or a computer which I have in my hardware laptop at my workplace. So exactly the same thing also we does in case of the engineering industries. So in case of Foxboro system, as I have mentioned, these servers or these normal operator workstations, they are installed with a dedicated operating system and some software need to be installed additionally. So for that, what we do, we have created a virtual image of those workstations, and those virtual images we simply keep in our laptop, the same laptop which is given to us by the company. We simply copy that VM image to our laptop, and in that laptop we have the VMware software installed, and from that VMware software we'll open the VM image file. So let me show you that how exactly we does it. So here on my laptop, I am going to share my whole laptop right now. Okay, so here I am sharing my whole screen. So right now I have minimized everything. So I have installed a software that is called name as VMware. I hope everybody is able to see this VMware Workstation Player. Okay, so if I open this VMware Workstation Player, on my left, you can see there are a couple of images are available. This is called as VM images. Okay, so these images are nothing just a completely prototype or a alias copy of any hardware computer. Okay, so this particular TRAW01, this is one of the virtual image of a application server of Foxboro DC System. So I am going to play this virtual machine right now. So once I click this play, it will open this virtual machine or it will open the virtual image on my laptop. So it is ultimately nothing, just you are opening one more laptop, completely operating system platform in a different laptop or in another laptop. So if you can see, it is now starting an operating system here. So once this operating system starts or when it opens, so on this, I can start installing all the software. Okay, or if it is what we usually do to reduce our work, we keep all the software installed on the VM image and we use the same image for different projects. So my image will be having all the software installed. Simply based on the project requirement, I have received the P&ID diagram. Okay, and based on the P&ID diagram, I will start working on my engineering and I will start creating my loops or logics or programming, coding, whatever you say. Okay, so fine. So right now, if you can see, my virtual image has opened. So this VM image, it is just like it is one operating system or it is another laptop. So on my left bottom, if you can see, there is something called as IS series is starting. So this particular VM image is already installed with all the Foxboro DC softwares. And whenever you start any application server of any Foxboro DC system, you will find this as default IA series starting. It means whatever the backend processes applications are there, all these executable files are now one by one, they are getting started. Once all the applications are executed, here it will display is IA series is ready and it will pop up with a DCS operating window, and I am waiting for that window. Once that window comes into the screen, we will discuss further. Meanwhile, if anybody has any question, please go ahead. Regarding this VM image, VM software, why we use it, how we use it, when we use it. If you have any question, please feel free to ask. This is really something very practical what you are going to do in the field of process automation. Like if you are joining into Honeywell, ABB, Foxboro, Yokogawa, okay, or Siemens or Rockwell, all these companies, they have this DCS system, and for right now every company is using VMware. Okay, it is not only with this process industries and also with the software companies that everyone is using VMware, because VMware is ultimately giving you the opportunity where you do not need to have a real hardware, and at the same time on your existing hardware, on your existing laptop, you can have a high-end configuration software platform where you can do all your work on the go. That's the benefit of using a VMware.
Hello.
Yes.
Sir, that hardware is turned on or it is okay to be turned off? Still, you can access all the things through your VMware.
Sorry, please come again. Your voice was not clear. Please come again.
Yeah, the hardware parts can be turned off, or you need to be turned on when you access remotely through the virtualization or VMware.
Okay, fine. You need not, you don't need to have anything to do with that hardware. What we have done, we have made a Xerox copy of that hardware software actually. So once the Xerox copy is there with you, it doesn't matter whether you have the original hardware on, off, whether it is with you, it is without you, it doesn't matter. You are not connecting to it. It is not remote desktop connection. In case of a remote desktop connection, the remote server need to be on. It has to be switched on and you need to connect it on the network. But in this case, it is different. What it is different, you have a server, you have created a VM image of that server that you have copied into a hard disk. And that VM image you are opening on the VMware platform where you are able to access all the softwares, whatever is installed in that particular server from where you have taken the VM.
Right, sir. Right. Thank you.
Okay, so usually it takes maybe 5 to 10 minutes of times, also depends on the speed capacity of your laptop, because my laptop is already loaded with a lot of applications, so it is taking quite a lot of time. So let it go. Meantime, what we are going to discuss is that how we do the engineering, or what is the starting point of engineering, or what is the end point of the engineering, what exactly we do. So now here, as we have discussed in the first slide, that in a process plant, you will have a lot of continuous control applications, okay, where you will have a level control, flow control, temperature control. So being a DCS engineer, you don't need to worry that what exactly is the loop over in the plant. What you need to know is that you must be able to understand a process instrumentation diagram, that is we call it as the PID. Okay, so understanding a process instrumentation diagram is very, very important for a DCS. Right now I do not have any PID diagram with me. It has been I'm not sure, because I do not have that particular hard disk with me where I have those the PID diagram. But yes, we can Google on it. That you can simply Google what is the different type of PID diagrams. We'll definitely get some. Okay, so this is something called as the P and ID diagram, process instrumentation or piping and instrumentation diagram. Also, in some of the EPC they used to call it as process. Some of the EPC they call it as P and ID. Now, I'm using one more new term that is called as EPC. What is again EPC? Now, let us say previously you have discussed a lot of things about Nalco power plant, okay, or the Nalco plant. So now, who has designed the whole plant? So definitely there is one third party who will be designing this plant. One of the example of a EPC is that EIL. Many of you might be knowing about EIL, Engineering India Limited. Engineering India Limited is a EPC who is responsible or who has designed all the government sector plants. Maybe it is NTPC, BPCL, IUCL, all those things. Similarly, you might have heard about a company name as Dow, DOW, Dow. Okay, who Dow, which plays a very important role in the stock exchange of USA, United States of America. So Dow is a very big group, or it's a very big company who works as a EPC. EPC stands for Engineering Procurement Center. So these EPCs are responsible to design these process and instrumentation diagrams. So every plant, whoever wants to implement this DCS system, they will be having this PID diagram. and this PID diagram, it will be shared with the DCS engineer. So they will say, this is our completely piping diagram or process diagram, and we want to have, or we want to develop the control loops for this process. So understanding this P&ID diagram is again a very critical role for DCS. But don't worry, I mean, you need not to have this idea initially or before going for an interview. These things will be given to you as a training or as a skill development whenever you join any of these company where you join DCS. Okay, but yes, my intention here is that you will be given training on this, that how to understand a P&ID diagram and what a P&ID diagram. And not only this, along with the P&ID diagram, customer will provide you a IO list, which we call as input output list. So in that input output list, they will provide you the complete series of inputs and output elements what they have in the plant. Okay, so here what you are going to do, ultimately you are going to create the complete logic for 1000, 2000, 3000 loops. So every loop will have an analog input, one PID and one analog output. Okay, not always only analog input, analog output. Also there may be some situations where you have discrete input and discrete output. So to design those PID blocks or to design this control loop, you need a platform or you need an environment where you can develop these engineering applications. So to do that, I will open the engineering development environment in case of Foxboro, which we call as ISCC. Okay, don't worry about these names. Okay, they are just vendor specific names. But for your understanding, what I am opening right now here is a engineering environment where you can develop some logic. That is my intention here. So here, whenever I want to develop some logic, if you can see here, it is asking me that for which processor you want to develop this logic. So my PC is already configured for one particular DCS architecture where we have these CPs. They are the control processor. If you remember, previously we discussed about the control processor, inside which ultimately we keep the programs or the function blocks. So here, this is our, let's develop some logic for the TRCP2. This is just a CP name what I have defined, and I'll say, okay. my image is taking or it is responding beyond expected time. So I have given a restart to it. Meantime, let's discuss about the PID function loop, and then we will, once the image starts, then we'll move to the software part, or I will show you that how to develop these function blocks over there. So if you can see on this particular presentation slide that here we have a process, okay, and this arrow mark here, it is wrongly directed arrow mark. I'm sorry about it. This has to be directed towards the output, okay. So this has to be on the other way around. Fine. Now on this process, before this process, you have some input transmitters, like let us say in this process you want to control level, you want to control temperature or flow, whatever. So to do that, you have a transmitter. So those transmitters may be a simple analog transmitters, or maybe display transmitters, or maybe Profibus, Fieldbus, hardware, whatever. And from there it is coming to the FBM, and from Fieldbus module, this comes to the analog input block. So this analog input block, this controller block, and this analog output block, these three are the part of the software, or they are the part of the engineering software where you will develop them. Okay. So this analog input block is responsible to read a value from one of the input channel of Fieldbus module, and they will do the signal conditioning based on your requirement, and they will provide the output to the PID block. And inside this PID block, whatever the proportional, integral, and derivative parameters you have defined, based on that, this PID will give an output, and that output will be given to the analog output block. Same way, analog output block will again do a necessary signal conditioning as per the requirement by the field, and that output will be coming out of the control processor, and this will be going to the Fieldbus module again. And from Fieldbus module, the signal is given to the field devices, that is ultimately a valve. So here, the functions provided Foxboro, here it is analog input block, controller block, and analog output block. Now, when I am saying one analog input block, so if you see here, the analog input block, this receives the value from the FBM, okay, and when it is receiving the value from a Fieldbus module, inside this analog block, what I need to mention, the name of the input module or the FBM and its channel. So here in case of Foxboro Dc System, every control processor, every Fieldbus module, they will be defined with a name, 6-character name. Okay, it may be it will be alphanumeric name. Okay, like a CP name could be TRCP01, one FBM name could be DICR01. Anything could be alphanumeric, but 6 number of letter or alphanumeric size. So here you will define that FBM name and the channel from where this input block will read the data, and from that this input block receives the value, and then it does the necessary signal conditioning, filtering, scaling, whatever you wish. And also you can define the alarming feature for the analog input block. What is this alarming feature? Here you can define that if any input value is going out of range, for example, for an analog input block, the value it has to receive from a range of 420 milliampere. But there are possibilities. If the transmitter starts malfunctioning, you may be receiving value more than 20 milliampere, or you might be receiving value less than 4 milliampere. So in those cases, you can define in the alarming set points that yes, I need to receive the value from 4 to 20 milliampere. In any case, if the value is received below 4 milliampere, I need to have a alarming signal on my analog input block. So with this, what will happen? From this analog input block, whatever the alarm comes, it will be displayed on a operator screen. So immediately operator will come to understand, yes, this particular analog transmitter is now malfunctioning, or it is not giving the appropriate output value. This is one of the way that how a DCS system, even if you do not have a smart transmitter, you will be, by simply using analog transmitters, you can have fault monitoring, or you can do the fault analysis of the transmitter just sitting in the control. This is one of the advantage of using Foxboro DCS system. Now, in Foxboro DCS system, whatever these blocks what we have, we call them as the function block. All these function blocks, they have more than 100 parameters which you can do setting or you can change. Okay, so as much as parameters you need to understand, you need to go through the document provided by the DC system where each and every parameter has some meaning, and based on that you can use those features as per the customer requirement. Okay, but here always remember, we do not just do like as I have mentioned that inside a CP you may have more than 6,000 7,000 function blocks. So you cannot just make one by one block, one parameter to adjust. They all will be done in a bulk. So that's what we call as a bulk generation. So while creating a bulk generation, some of the parameters, whatever the common parameter, that will be created in a bulk manner. And once the bulk generation is complete, for individual loop, if any specific requirements are there by a customer, you can change those parameters in a later stage also. After the analog input block, whatever the output of the analog input is there, that output is given to the measurement parameter of the PID block. Now from the PID block, you can define the set point. This set point is defined by the operator. So at any point of time, an operator can change the set point of this PID block, and whatever the input, the PID block will ultimately calculate the difference between the set point and the input, and that is this difference which is called as the error. Based on the error, the PID will give the output. Here in this case, there is something mentioned as remote set point. So what is remote set point? The remote set point is something, if you want to provide a set point to this PID block from some other PID blocks output. Okay, for example, you have cascade control applications. Okay, you might have studied about cascade control system, right? Okay, a PID control inside another PID, right? So in case of a cascade control, the output of a PID block will be given as a set point to another PID, that is cascade control. So if there is any cascade control loop applications are required, so you can use in that case this remote set point parameter, from where you have to connect the output of the relevant or respective PID block from where you want to take the output, and that will be considered here as a set point. So that is called as remote set point. So any point of time, let us say you have one simple closed loop system where you are taking the input, you are giving it to PID and taking the output. But depending on the functionality or requirement, you want to change the closed loop control system into cascade control. In that case, simply it will be go with one single button click by the operator. Operator will simply change the mode to remote. Once it changes the mode to remote, whatever the connection has been given to this remote set point, that value will be considered by the PID, and the PID will be start giving the output based on this calculation, difference of this measure and the remote set point value. That's how the PID block can be designed in this case of Foxboro DC system. Now, whatever the output is coming out of the PID, that is next going to the analog output block. So again, in the analog output block, in a similar way, as we define the field bus module name and the channel from where they read the value, in case of analog output module, we define the field bus module and the channel number to where the signal has to go. Ultimately, to this particular field bus module, the field element or the output element which is located in the field, maybe it is a pump, it is a valve, it is a solenoid valve, whatever it is, or it is a alarming lamp, whatever it is connected to this field bus module, and it will be receiving signal from the field bus module. So similar way, whatever the output is coming from the PID, you can do the necessary signal conditioning by using this AOUT block, and from the AOUT block, the signal will be coming out of the control processor, then going to the FBM, and from there it will going to the field. So that's how one completely closed loop, one analog input block, one analog output block, and one PID, they combinedly can be connected to create one closed loop control system. Okay. Anyone has any question? On this closed loop control system, or how we define the different blocks?
And you have any question, please ask.
Okay, I think I have already reached the scheduled time, but I am still trying to start my VM image. I'm trying to start now another image so that I can show you some real-time phase of a DCS system and engineering environment. Meantime, if you have any question about what are the topics we have discussed so far, you are most welcome to come up with your questions. Please go ahead. Do not hesitate. You can also ask anything which is relevant to this topic or may not be relevant. Please go ahead.
Sir, I have a doubt.
Yes.
Sir, I have doubt on CNC control, sir.
Okay.
Sir, like how CNC control are monitored in using DCS.
Okay, CLC means what exactly? Can you define CLC? What you are saying?
Sir, computer numerical control.
Huh?
Computer numerical control, like CNC milling machine, and all we are saying, right?
Computer numeric. Please tell me something about it, because I have never used such control applications in but particularly for the refineries or the power plant. Can you tell me something about it? Definitely, I'll help you on this.
Okay.
What exactly is this?
Sir, 1 minute. I'll say it, like CNC control application, like laser engraving, and in the manufacturing industries we use more, sir. Laser engraving, metal cutting.
Okay. Yes. I got it. Yes. So in that, what exactly you want to know?
No, sir. Like how such controls are monitored, and the controller is PLC, or like there are separate controllers for that we are using.
Okay. Now see, here there are two things. For the process control application, either you can use a PLC or you can use a DCS. Okay. Now, what is the difference between these two is that ultimately PLC also can do the same thing what your DCS system is doing. But the benefit is that, to understand this, let us say you are going to buy a desktop PC from the market. So when you are going to buy a desktop PC, you have two options. Either you can buy a branded PC or you can buy a assembled PC, right? Am I right?
Yes, sir.
Yes. So when you buy a assembled PC, the price is cheaper. Am I right?
Yes, sir.
Yes. But when you buy a branded desktop PC, the price is very, very higher. Yes or no?
Yes, sir.
Okay. But ultimately, they both will fulfill your purpose. But what is the drawback with the assembled PC? Because you bought a keyboard from one company, you bought a motherboard from one company, you bought the desktop screen from one company. Okay. And you have assembled it. Fine, it is working today. Right now, everything is good. Today you have installed Windows 7 operating system. Tomorrow what happens? Windows 7 operating system will obsolete. Microsoft will stop supporting the Windows 7 operating system. Then, to install the Windows 8 operating system on your laptop, all the other hardwares, your motherboard, your mouse, your keypad, your display, everything has to be compatible with the Windows 8 operating system. Yes or no?
Yes, sir. Obviously.
If they do not compatible, they will not work. The same way also, the same example or the same way, the difference is there with the DCS system and a PLC. You can, let us say I will buy the PLCs from Rockwell. I will buy 10 PLC and I will buy a HMI from Rockwell. I will buy a history application from Wonderware. I will buy a SCADA application from Wonderware. I will integrate and I'll start working. Tomorrow, suddenly what will happen? Rockwell will upgrade their firmware on the CPU, and that upgraded firmware will not support my HMI, will not support my SCADA system, will not support my historian. Then Rockwell is not responsible for that. Ultimately, you have to run behind all these third parties. So this creates a lot of difficulty for the customer. For that purpose, customer uses a DCS system. Now, by using a DCS system, the loop what you are asking, either it is continuous or it is discrete. Both can be done by PLC, both can by DCS. In my point of view or with my experience, ultimately there is no difference between these processors. PLC processors are also equally capable to do the continuous controlling, but most of the continuous control loops, wherever you have process plant like refinery, where you have huge control applications, there the DCS is preferred. So that's why the industries what you're talking about, maybe the cutting industries or the manufacturing industry, they mostly go with the PLC because that fulfills the requirement. But when it comes to refinery or power plant like NALCO, NTPC, BPCL, they have huge huge process applications where huge number of IOs will be there. 10,000, 15,000, 20,000 input output will be there. So for that, you need to have a DCS. That is the basic reason behind it. So ultimately, your answer is that you can go with PLC, you can go with DCS, no problem. And ultimately, whatever we have discussed, analog input, digital input, analog output, digital output, PID block, these all concepts are same wherever you use it. There is no changes on this.
Okay, thank you, sir.
Thank you, sir, for your valuable ideas on this topic. So it
Okay.
has given us a very
And and I'm really sorry that my VMM is not able to start because my problem is that my laptop is connected to internet and my VMM is creating some issue when it is connected to the internet because all my licenses are creating problem because this software this I have installed 3 years back, so all the licenses are expired. So when I'm connecting to the internet, I am facing some issue, and I'm really sorry about it because I couldn't make it during this short session. But definitely in future, if some sessions are planned, we'll discuss about it.
Yes, sir. Thank you so much. So we will meet tomorrow at the same time. Thank you, everyone.
Thank you, sir.